Welcome back everyone to part 5 of section 4.2, where I explain how to treat the semi-classical limit within the context of Weyl quantization. One of the initial things that I started this mini course with is that the systems that we are interested in are typically exposed to magnetic fields. Or at least the question of the dependence of conductivity on the magnetic field is a crucial one. And so you could ask the question, how does Weyl calculus accommodate magnetic fields? And let me start first with the corresponding classical system. So here there are actually two paths which are equivalent. And the first path is minimal substitution. So basically, this is the de facto standard. So here we're always considering a magnetic field B. And depending on our needs, we shall think of B as a two-form, as a closed two-form. Or we can also think of it in terms of its matrix entries. And associated to B, you can find many vector potentials. So vector potentials are highly non-unique. So here a vector potential is a one form, which I will just tacitly identify with a vector field. And the two are related by, in terms of differential forms, the exterior derivative of the vector potential has to be the magnetic field. And on the level of functions on phase space, what you do is minimal substitution. So you replace F by FA, and FA, there you simply, let me maybe move this down here so it's more easily visible. So here you simply, you do nothing to the first coordinate, to the spatial coordinate, but you replace xi by xi minus a of x. And the way you should think about this is only kinetic momentum and this is just xi a. So in this, using the definition below, this is just xi minus a of x. Only kinetic momentum is an observable quantity. Naked momentum, so only xi itself, so only this here, is no longer something you can measure in experiment. Only the kinetic momentum xi a is something that you can measure. And then, okay, the second path is to integrate the magnetic field into the symplectic structure. So those are big words. Let me explain what I mean by them in turn. So here this means that if I derive the equations of motion, I get the Lorentz force term for free. So the Lorentz force appears automatically by simply integrating it into the symplectic structure. So you can write out the symplectic form. You can think of it as a matrix that multiplies the time derivative, and on the right hand side you have the xi gradient and the x gradient and the xi gradient of h. And now to get the right combinations of signs, so the x gradient of h needs to appears in the equation for xi dot, and it needs to be multiplied with a -1. So we have a minus identity matrix here. The xi gradient appears in the equation for x dot. So we have a plus identity here. And the Lorentz force term appears for the magnetic term. So let me write the B here. So this is the right-hand side, the left-hand side simply then equals to B times x dot minus xi dot is equal to the gradient of h and x, where h is the Hamiltonian, and then for the other one we simply get x dot. And once you solve for x dot and for xi dot, then you just arrive at the usual equations. So the point here is that there is a geometric picture to all of this. So that you obtain just the Lorentz force law. All right, so these two approaches are equivalent, and the way to see this is to compute the equation of motion for kinetic momentum. So let me just use one of the coordinates and let me compute the time derivative here. So this is equal to the time derivative of xij, which is exactly what you think it is, minus the time derivative of aj. And now, okay, for the first one, I just plug in the canonical answer, and that is minus the dxj gradient of the minimally substituted Hamiltonian, right? Because the energy is an observable and we need to use minimal substitution. And then we get a second term, because when we derive A, we have to derive it with respect to x. So we get dxn aj times xn dot. So when we compute this derivative here, the thing is we should actually use total derivatives, right? So, and because of minimal substitution, we get two terms. The first one comes from simply the derivative in the first argument, but then we have to minimally substitute. So this is just acting on this first component, but then there is a contribution by the derivative on the second component. So we get minus d psi. Okay, now I need a sum from n equals to 0 to d, and then I have d psi n of h minimally substituted times, and now we have to look at what we get. Well, we have a minus sign, but then there's also a minus sign here. Well, sorry, in the minimal substitution. So we actually get a plus sign here, and then we get d xj an. And then we have to subtract the term from before. So if you look very carefully, then you already see that, okay, this here, the first term is just x dot, the nth component of x dot, of the velocity. And then we have two terms that are almost the same. It's just that the components here are reversed. And that's exactly what we want, because this gives us the magnetic field, the Jn component of the magnetic field. So we get minus dxj h minimally substituted plus the sum over n. Sorry, the sum goes from 1, not from 0. Up until d, and then I combine the let me color them, this here and this here, into the magnetic field. So this is exactly identical times x dot n. And now if you just compare and of course the equation of motion for x dot is not modified, and that is because the the minimal substitution, the minimally substituted operator here, total and partial derivative with respect to psi coincide. So what you get is the exact same equation of motion for kinetic momentum as for momentum here with this modified symplectic form, which is just another way of saying that if you integrate the magnetic field into the symplectic structure, you are using kinetic momentum. But the advantage is that with the second approach, you never have to worry about choosing a vector potential. Nevertheless, the first approach is the one that's more commonly used. Let me also add something about the Poisson bracket, because the Poisson bracket tells you something about the nature of observables. So in the presence of the magnetic field, you have a magnetic Poisson bracket. And if you think about it a little bit, the magnetic Poisson bracket of F and G, so here I'm adding a B to indicate that's the magnetic Poisson bracket. That's just the usual Poisson bracket. So the first two terms should be familiar to you. And then I'm adding a term. I should write out the sum. So here you have to sum over the components. And here you have Bjn, and then you take the derivative with respect to psi j of F and the derivative with respect to psi n of G. And the important thing is that this satisfies commutation relations, well, the analog of commutation relations. Well, in the position variable, we get nothing new. These guys just commute. That's because, again, here, you always have a mix. I have a small typo here, of course. Here, I meant to take the gradient with respect to psi. So the non-magnetic term, you always have a psi derivative paired with an x derivative, and that means that this does not contribute to the Poisson bracket of different components of x, and it does also not contribute to the commutator, to the Poisson bracket of different components of momenta, but the second term does, right? So here what you get is basically delta contributions. So what you get in the end is minus Bjn, which for the systems we're interested in is importantly different from zero. At least some of the components are. And this is important, right? So this is an essential difference to the standard systems we considered before. And then for the mixed Poisson bracket, only the first, the non-magnetic term contributes, and we get a minus delta Jn as before. And now let's look at the quantum side. And here, there is a lot of focus on minimal substitution because the two approaches are no longer equivalent. So let me get a little bit jargony here. If we want to so whenever we describe a quantum system, we have to choose a representation. And when we are interested in magnetic systems, then part and parcel of choosing a representation is choosing a gauge. So choice of representation implies a choice of gauge. But still, all essential properties of the physical system must be preserved because of a second thing, that's gauge covariance. And that's just saying that if we change gauge, this corresponds to a unitary transformation, and a change of representation is exactly implemented by a unitary. And because essential properties of physical systems are described only modulo a unitary, so for example the spectrum or the spectral components, the same is true for magnetic fields. All essential properties of the system only depend on the magnetic field. So let me make this mathematically precise. So the building block operators are now position. Okay, we change nothing about position, of course, just like in the classical system. And momentum, where now we have to choose a vector potential A. And this is just minus I times the derivative in the jth direction of psi minus A of epsilon x times psi of x. And of course, here we're choosing the jth component of the vector potential. So a gauge transform, or let's say an equivalent gauge, A prime, which is just A plus d chi, where chi is a zero form or a scalar function. So let's assume it's also smooth and polynomially bounded, real valued, but scalar valued. Then the operator PA prime j, which is minus I gradient minus A prime evaluated at epsilon x. Sorry, in this case it's A of epsilon x minus epsilon, the gradient of chi epsilon x. And this here is unitarily equivalent to the original operator here. how do we see this? Well, with a bit of grid and computation, you can convince yourself that so this here this guy here is just our position operator Q, and to be consistent, I should put hats on top to indicate I view them as multiplication operators. And this is the same as adjoining with e to the minus I chi evaluated at Q. And because evidently this operator here is unitary, for example, the spectrum and the spectral components of these two operators are the same because they only depend on the invertibility, and hence, this doesn't really matter whether or not in what representation you are. Then there are things that change covariantly, like the domain. So the domain of the operator in the new gauge is the domain of the previous operator, but you have to it's the range of the domain of the previous operator under the unitary. So this way you have a relationship between the domains and so forth. So things changed in a controlled way. So let me just say, so this here, this is important. This relation here, this is gauge covariance. So let me write this pictorially. So for example, the spectrum of, let's say, PAJ, the jth component, is a set that only depends on the magnetic field B. So this is what I mean pictorially here. And indeed, this is essentially true of all other properties, because, for example, if PA is a self-adjoint operator, then also the operator in the new gauge is a self-adjoint operator with the transformed domain, and so forth. So what we would like is that our quantization rule should be gauge covariant. So just to write this down one more time, that means if I replace A by A plus epsilon gradient chi of f, where f is a suitable function. Suitable just means, well, what I write down should be well-defined, for example, as an operator on L2, then this is equal to e to the minus I chi of q op A of f e to the, sorry, I think the plus belongs here, e to the minus I q. And now what we can do is we can just attempt what has been done up until 1990. Well, effectively speaking, in the math phys community up until the mid 2000s, early to mid 2000s. And that is defined, and I'm going to use a different symbol here on purpose, where the A is on the bottom. What I'm doing here is I'm just combining Weyl quantization as I've introduced it before, but I'm applying it to the minimally substituted function fa. And here it turns out that, and that's why people, I guess, didn't realize it. Okay, let me use black. So if f of x and xi is equal to, let's call it h of xi plus v of x, where h is a polynomial of degree less than or equal to 2 in xi, it actually is gauge covariant. But, and this is the downside, but if it does not have this nice form, it is not gauge covariant. So that's why people didn't notice earlier, I guess. And this means that if you do some construction, let's say some perturbation expansion, using the asymptotic expansion of the Weyl product for minimally substituted symbols, then you have to impose conditions not just on B, but on A. And higher order terms actually depend on the vector potential. And this is, of course, bad because it breaks this the paradigm that all physical properties of your system only depend on the magnetic field rather than the choice of vector potential. So that's why the second attempt is bad, but I've presented regular Weyl calculus in such a way that you can already guess the good solution. So let me make attempt 1 red, because this is turns out to be a bad idea, and let's make attempt 2 green, because this is a good idea. And what we do here is we define the magnetic Weyl system not with the usual momentum operator, but with the kinetic momentum operator. So the difference, just in case you have a hard time seeing it, let me make it orange, is here. So here you're using the kinetic momentum. And now this operator is defined by functional calculus, and that means it inherits the gauge covariance of Q, which is in fact gauge invariant, and PA. And then, okay, what do we need to do is we just need to define magnetic Weyl calculus in the usual way. So the magnetic Weyl quantization remember the trick of thinking about magnetic Weyl quantization or of Weyl quantization as taking the symplectic Fourier transform twice. So this is akin to evaluating the function that you're quantizing at the operator Q and the operator PA, even though, of course, this that doesn't really make sense, or rather it is defined by whatever is on the right hand side. But I think as a way to gain an intuition, it's the right idea. And then, okay, we have to write out the first symplectic Fourier transform of X. And then we replace the regular non-magnetic Weyl system by the magnetic one. And that's it. So this is gauge covariant by construction. Importantly, even though the proofs are trickier because you have magnetic phase factors appearing in places and so forth, if you make the assumption, and this is the assumption that I've imposed before on the magnetic fields and vector potentials, the components of the magnetic field shall be smooth, bounded, and have bounded derivatives to any order. So maybe this, maybe I'll use a different color. So this is the B here. So the B just means that the components of the magnetic field are bounded, smooth, and have bounded derivatives to any order. And then, of course, the vector potentials, they don't need to be bounded. In fact, you don't want this to be true, because then this would place restrictions on the magnetic field. Instead, it suffices if they're smooth and polynomially bounded. So you're working with Schwartz functions and tempered distributions. So you can think of polynomially bounded functions as tempered distributions. And of course, the second restriction is that the exterior derivative of A needs to be equal to B, right? This is what it means for A to be a vector potential for B. And then under these assumptions, you, for example, have that when you're quantizing a function from S0 rho, which can be embedded into S0, 0, which is nothing but the the bounded smooth functions with bounded derivatives to any order on phase space. Then the magnetic covariant quantization defines a bounded operator. So this is the magnetic version of the Calderon-Vaillancourt theorem. And then you also similarly have self-adjointness results for elliptic symbols. So the most non-magnetic results have a magnetic analog. I will not go into details here. I recommend you have a look, for example, at my PhD thesis, where I list some of the literature on the subject. I could introduce more, so there were important papers by Iftimie, Montoyo, and Purice. There were at least 3 of them. There is an important paper by Purice, Cornian, and Helfer. But you know, I don't want to overburden you. So similarly, you can also look at the magnetic, or define a magnetic Weyl product. And importantly, as the notation already suggests, the gauge covariance condition, property, sorry, it's not a condition, it's a property of our covariant quantization. It's defined in exactly the same way. You just pull back the operator product, and because of gauge covariance, the product on the level of functions on phase space or distributions on phase space only depends on the magnetic field, which is exactly what you would expect. And that means that, for example, the associated perturbation expansions also only depend on the magnetic field. So, of course, there's an explicit formula, but I don't think it is necessary. I mean, it contains an additional phase factor that is due to magnetic flux through triangles with varying corners and so forth. But the point is, it depends on B. You have similar results. So, for example, you have a composition, a nice composition properties for Hörmander symbols. So the Weyl product of 2 Hörmander class symbols is again a Hörmander class symbol where the order is the sum of the orders, and this map is continuous. And you also have an asymptotic expansion. So, for example, for Hörmander symbols or for Schwarz functions. And just as before, and this is the important point that I want to impress upon you, the 0th order term in the semiclassical parameter is just, again, the pointwise product. And then the order epsilon term looks almost identical to what we had before, but of course now we have to use the magnetic Poisson bracket rather than the non-magnetic one. So here, this is the important difference, and this is, if you look towards the semi-classical limit already, this is exactly what you want, because remember, morally speaking, this here, the Poisson bracket corresponds to I divided by epsilon times the commutator of position and momentum operators, and we should get exactly the same type of structure here, namely that the kinetic momentum operator, and indeed it does. So for example, these guys here, they satisfy, as you would expect, I divided by epsilon of qj and qn is 0. I divided by epsilon PAJ and PAN is equal to minus BJN of Q, and then okay. It's not multiplied by epsilon because you have factored this out, so to speak. And then you have the usual canonical commutation, or the same commutation relations as in the canonical case, rather. Namely, you get minus delta Jn. So this perfectly resembles the Poisson bracket, and with this in mind, it's not at all surprising that in the asymptotic expansion you have to use the magnetic Poisson bracket. That's exactly what you want. And then let me just mention this, and I will not give even many more properties. There's also a magnetic Wigner transform. Now, all of this might seem a bit vague, but the takeaway message should be for you that there exists a magnetic Weyl calculus, a magnetic pseudodifferential calculus that is optimized for systems with magnetic fields. The central piece here is the gauge covariance of the quantization rule, which ensures that all properties only depend on the choice on the properties of the magnetic field. And lastly, in view, if we think about the semi-classical limit, also here the magnetic field arises quite naturally, and the way we should think about this is that magnetic Weyl calculus uses position and kinetic momentum as its variables. All right, that's it with part 5. Now the next bit is to convert this pseudo-theorem and pseudo-proof into a proper theorem with a proper proof.